Today we are going to talk about, we are going to continue our discussion on sorting. We'll begin with radix sort, then we are going to look at bucket sort. In-place sorting is something that we've seen before. Which are the examples that we know of in-place sorting? Heap sort, quick sort, insertion sort, selection sort, bubble sort. Bubble sort we have not done. Okay, we are going to look at this, we are going to see which is in place and which is not in place, right? Not all of these are in place, what you just said. Okay, we are going to see, and then we are going to finally look at how fast we can sort. Can we do better than what we've been discussing so far? Okay, so what's radix sort? So in radix sort, we are going to look at the keys that we are going to sort. So recall that in all the other sorting algorithms, we are only comparing the keys. We are not looking at what the actual structure of the keys is. It doesn't really matter if the keys are people, provided you have a way of comparing two people, two persons, right? If you have a comparator function which gives two persons can say one is less than the other, then you can also sort people. Yeah, but today, or in radix sort, we are going to look at the key itself that we are trying to solve, that we are trying to sort, the collection of keys. So we are going to assume that the keys are represented in some base m number system, right? And m is called the radix. If m equals 2, then the keys are essentially in binary, right? It's base 2. Okay, so this could be an example. 9 is 1001 in binary, right, in base 2, and we are going to use this representation of 9 to do the sorting for us. I can represent 9 in base, some other base also, base 3, let's say, right? Okay, so then m would become 3, and I would get, you know, I can still use that to do the sorting, and we'll see how. Yeah. Okay. And in radix sorting, the sorting is done by comparing bits in the same position, right? So instead of comparing numbers, instead of comparing 9 with 11, we are not going to compare 9 and 11, we are just going to compare the bits in 9 and 11. And which bits? We are going to, let's say look at the bit at position 3, and we are going to compare them. Okay, we'll see all of that in a second. And this idea can be extended when the keys are, let's say, alphanumeric strings also, right? Not just binary numbers, not just numbers like this, but alphanumeric strings, so names of people or some such thing. You can also use the same idea to do sorting on that, and we'll see how. Okay, so I'm going to talk of two variants on radix sort. One is called the radix exchange sort. So what we are going to do in radix exchange sort is we are going to examine the bits. So I'm going to assume now that the keys that we are trying to sort are some numbers represented in binary for us. Okay, and I'm going to examine the bits from left to right. So let's assume also that each of the numbers that are given to us have a fixed representation, right? They are expressed in the same number of bits, right? So that can always be done. If the largest number in your collection is, let's say, some n, then you need basically log n bits to represent that number, that largest number, and so with log n bits you can express all the other numbers in log n bits, and that would be the number of bits that you would use to represent all the numbers in the collection you have. So we are going to sort the array with respect to the leftmost bit first, right? So suppose the numbers are sitting in this array, right, and the leftmost bit of this number, so it really doesn't matter what these other bits are. I'm just looking at the leftmost bit of each of these numbers. So this is the first number, this row, the second number is in this row, so there are 5 numbers, 5 rows. Yeah, I'm going to look at the leftmost bit, and I'm going to sort the numbers according to this bit, which means that these are 2 zeros, so they come first. So this number goes at this position, this number goes at this position, and the ones come later. So this will go here, this would go next, and this would be the last number. This is what I would do. Sort according to the leftmost bit, and since the bit can have only 2 different values, it's easy. The zeros come before the ones. Clear to everyone? And now we partition this array, right? So this is not yet sorted, this set of numbers is not sorted, but now if I will now divide it into two parts. This is the top subarray and the bottom subarray, right, and I am going to now sort this top subarray independently of the bottom subarray, right. So what do I mean by sort the top subarray? I will just look at these numbers, forget this bit, because this bit is the same for all of these numbers, so it will not make any difference in the value of the number. I will just forget this bit. Similarly, when I am sorting this, I will forget this bit. What does it mean to forget this bit when I am sorting these numbers? So I am saying I would take the number and remove and subtract some number from that. What is that number? If these were k bits number, I am subtracting 2 to the k from that number. So if I subtract 2 to the k from each of the numbers and then sort them, then it is the same as sorting the original collection of numbers, it does not make a difference. Yeah. So I can sort this bottom subarray independently of the top subarray, and then I just put them together and I would get a sorted sequence, right. So it is a divide and conquer algorithm once again. Yeah. There is a divide step in which the zeros come before the ones, there is a conquer step, right, and the combine step is trivial here. So the conquer step, this is the recursion. So we will recursively sort the top subarray ignoring the leftmost bit, we will recursively sort the bottom subarray ignoring the leftmost bit once again. And how are we going to sort these? Using the same idea. We are going to partition this using the second leftmost bit or this leftmost bit and so on and on. So how much time does it take to sort these n bit numbers then? So I claim it takes order bn time if I have n numbers and b bits. Why is it thick? Why can you do it in so much time? Pardon? Number of bits is log n. Is the number of bits log n? Log of the largest number. The largest number need not be n. It could be much larger than n, it could be much smaller than n.
No, so basically, so b is equal to log n, because if you are assuming the keys to be non-negative integers,
yeah,
then the number of keys can be at most the largest.
N is only the number of
n is the number of numbers and not the largest number.
Exactly, sir. So number of keys n is at most the largest number. If you are
Number of keys is at most the largest number. This statement is not true. You could have duplicates,
the largest number.
and also the largest number can be much larger than the number of keys, right?
Yeah, that's
20,000. 1 to 20,000 is
Okay, great. So we will continue this discussion later. So I claim to sort n b bit numbers, you will require order bn time. And why is this? Let's try and understand this. Right? Can I write a recurrence for this? Can someone write a recurrence for this? Okay, let's write a recurrence. Let me switch and write a recurrence. So T of n comma b, why comma b?
Because the
Number of bits is the time to sort n b bit numbers. Yeah, let's say this is T of n comma b. What is this equal to?
n minus I, comma b minus 1, T of n minus I, comma
Right. So we are going to partition these n numbers into two pieces. This was the top subarray. Let's say this has I numbers in it, and the remaining would be n minus I, right? Yes. Now how much time does it take to sort these I numbers? How much time does it take to sort these I numbers? Because we are going to do it recursively. So it should be T of I comma b minus 1. That's important, the b minus 1. Why is it important? Because we are going to ignore the leftmost bit, because the leftmost bit is going to be the same for all of these numbers. And the time required to sort the other n minus I numbers is n minus I comma b minus 1 plus something more. How much time? Because I had to spend some time to partition these numbers, right? The numbers in which the leftmost bit was a 0 come before the numbers in which the leftmost bit was a 1, right? So they had to be rearranged, right? So for each, yeah, and that can be done in order n time, and this is the kind of a recurrence we would get. Okay. Now what is the solution for this recurrence? Anyone? What's the solution to this recurrence? Bn. No, it's perfectly right, right? If you're saying Bn, let's substitute. So this is the third method we had talked about, right? Solving recurrences by guessing a solution and substituting that solution and actually verifying whether it's true or not.
Shouldn't it be sigma and
Let's see what should be, right? Let's not worry too much about it. Let's see. Suppose T of n comma b was equal to b of n. Maybe I am wrong. Let's see whether I am right. Right? So what is my right hand side then? So the right hand side equals I, because n is I, times b minus 1 plus n minus I times b minus 1 plus n, which is this part is b minus 1 times I plus n minus I plus n, b minus 1 times n plus n, which is bn, which is also our left hand side. So this is correct. This is a solution to this recurrence. No harm. Okay. So this is the time taken, and we'll see other ways of arguing the same thing.
to find the time, otherwise we'll have to put a sigma over it and take the average from I for all values of I.
No, we don't have to do that. This would be the same for all choices of I. We don't have to do any averaging here.
But when we did quicksort thing,
That was because we were doing a randomized quicksort. We were computing the expected time.
But in this case also I is going
I
to
can
vary.
be anything.
I can vary, but what the whole point is that no matter what I is, it will always be the same. There, depending upon what I were, the time would be different, and so we were computing the average. If we tried to compute the average here, you would still get the same. The point is, it's always the same no matter what I is.
But sir, if we are solving this with second method, like where we put the recursive, then we have to go for
No, even then you don't have to go. If you do repeated substitution, once again you will see, of course it will be more complicated, which is why I did not do that method here. Yeah, you can also solve it by repeated substitution and you'll get the same answer. Right? It's just that you will have to keep track of what i's you used in the various points in the recursion, and that will make it a bit more cumbersome, but you'll get the same solution. Yeah, these are all b bit numbers. That's what we assume. The maximum number of bits is b, exactly. N has to be less than or equal to 2 to the power b. No, this is not true. I have nowhere said these are distinct numbers. I could have repetitions. Yeah.
So can't we just say that we have b bits, and for every bit we are doing n comparisons?
Yeah, so that would be one way of arguing it. I just wanted you to show you how to solve recurrence relations also, right? There could be many ways of arguing the same thing. Yeah, that's one argument. Okay, everyone understands what the algorithm is. Yes. How do you combine in this divide and conquer step? We don't need to combine. Once we have sorted this top subarray and we have sorted this bottom subarray, we just put all the numbers are b bit, exactly. Here, that's why this is all, uniform. That's why I said you will take the largest number, see how many bits you need to represent that, and you will use that many bits to represent every number. Otherwise this does not work. How will we? You just pad it with zeros to the left. If 8 is 1 0 0 0, 4 bits, then 2 would be 0 0 1 0, 4 bits. Okay? Great. So let's continue.
So what about negative?
we'll not worry about negative numbers right now, right? So if you had negative numbers and positive numbers, what would you do? So first split the numbers into negatives and positives, sort them separately and put them together, right? Why make life more complicated than that, right? You can always sort them separately. Yeah. No, that will not happen. Okay, we'll see more examples and it will be clear. Great. So in the previous slide I said that you will have your zeros before your ones, right? That was the first step we did. Let me go back. Right, यहाँ पे हमने क्या किया? We took these numbers and we changed this so that you had all the zeros appearing before the numbers in which the leftmost bit was a 0 appearing before the numbers in which the leftmost bit was a 1, right? We did this kind of a partition. Yeah, how do you do this quickly, right? If you recall in my recurrence I wrote order n for this and you did not, right, raise a ruckus on that, right? So the point is we can use the partitioning algorithm that we employed in quicksort to do this, right? What does that mean? We'll scan from top to down, finding the first key with a 1 in the leftmost bit, and from bottom to up finding the first key with a 0 in the leftmost bit and swap them. Yeah, the same kind of a technique we use for quicksort, and we'll exchange these keys, right? And we'll keep doing this until the scan indices exchange, so that we know that there are zeros above and ones below. And how much time did this take? At most the size of the array. Okay? So in this manner we can do the partition and then we can just call it recursively, right? And we'll get a time of order nb. So that's what we are doing here. We are scanning from the top to bottom. So this is the first place we find a 1, this is the first place we find a 0. We swap them. 0 comes here, 1 comes here, right? And then the next index would be this one, right? And the next here would be this 0. So we'll also scan them and we would get this, and now we are done. So what's happening? How is this different or related to quicksort? So I'll come to that in a minute, but before that see what we are doing at each step. Suppose these are the numbers before we sort them. What does this mean? Pardon? Right, these are the numbers. The first number in my array is this. Let's say this is the value, the y coordinate is the value of the number, right? This is the number, the second number is this is the third, this is the fourth, this is the fifth, this is the sixth. So what I am doing at the first step is that I am partitioning the numbers according to numbers which are more than 2 to the b minus 1 and numbers which are less than 2 to the b minus 1. The numbers which are less than 2 to the b, why 2 to the b minus 1? Because the first bit, the most significant bit we are saying should be a 1. They will come together, and the ones for which it is a 0 they will come together. Yeah, so I am partitioning the numbers according to 2 to the b minus 1. Those numbers whose value is more than 2 to the b minus 1, I am moving it to the right part of my array, right? So this is what's happening. These are the numbers with values more than 2 to the b minus 1, so they are in the right part of my array, and the numbers which are less than 2 to the b minus 1, they are in the left part of my array, right? And I repeat this on this one, right? So once again I am going to divide this up, and now I am going to consider the numbers here which are larger than 2 to the b minus 1 plus 2 to the b minus 2 essentially, right? Within this part of course more than 2 to the b minus 2 after I ignore the leftmost bit, but otherwise, so we keep doing this and eventually we will get something like this, right, which corresponds to a sorted sequence. So this is pictorially what's happening, right, but you understand the algorithm. Okay, now how does this compare to quicksort? Both the algorithms partition the array, both recursively sort the subarrays. So the structure is very similar. The difference is in the way we partition, right? In the case of radix exchange sort, we are partitioning with respect to not a pivot element, but with respect to a fixed quantity. We are saying anything more than 2 to the b minus 1 goes there, in the bottom half of the array. Anything less than 2 to the b minus 1 goes in the upper part of the array, right. So, it is the method of partitioning which makes the difference. In the radix exchange, divide the array based on whether the number is larger than 2 to the b minus 1 or less than, while in quicksort we are partitioning based on a pivot element. The difference is also in the time complexity. For radix exchange, we argued just now that the time complexity is order bn, and for quicksort we argued that the average case is n log n, right. So, sometimes this might be a better scheme, sometimes this might be a better scheme, depending upon what the value of b is for you. Yeah, great. So, that was a radix exchange sort where we were exchanging the elements in the array. So, I am going to look at another version of radix sort. The principle is the same, right, but this is also another way of implementing radix sort.
So you said that quicksort can be better.
Quicksort can be better, yeah, when b is larger than log n. B can be larger than log n, right. You can have one number, you can have numbers which are 2, 3, 7, 11 and one number which is 1,000,000 and 3. Now, you need a huge number of bits because there is one very large number, right. So, that b would be much larger than log n then, because the number of numbers is very small, but the largest number is very large, so that the number of bits you require to do your sorting is large. Yeah, great. So, we will continue. This is another version, as I said, of radix sort, straight radix sort. So, we are going to examine once again the bits from right to left now, not from left to right, but from right to left. And we are going to, so the 0 is the k equals 0 corresponds to the rightmost bit now, right, the least significant bit, also called the least significant bit, right. So, k equals 0 is the least significant bit and b minus 1 is the most significant bit, and we are going to sort the array based on this bit, the kth bit, in a stable way. So, sort the array in a stable way, looking at only at the kth bit. Okay, let us see what this means. Do you understand what stable way means? No, great. We will come to that on the next slide. Yeah, but let me show you what this is. This is the collection of numbers you have. What the algorithm is. You are first going to look at the rightmost bit, right, and you are going to sort these numbers based on the rightmost bit. So, as you can see, after you sorted them, you first have the numbers which have the rightmost bit as 0, and then you have the numbers which have the rightmost bit as a 1. Then you sort these numbers based on the second leftmost bit, on the second rightmost bit, right. So, this corresponds to k equals 1. So, you are sorting them based on this, and then finally you are sorting these numbers based on this. And what will happen at the end is that you will have a sorted sequence. Yeah. So, as you can see, this is originally non-sorted, and what you have here is a sorted sequence. So, why is this magic happening? So, you understand the algorithm. Take the rightmost bit, sort the numbers based on that, which means that just restrict your attention to the rightmost bit. Anything that is a 0 comes before everything that is a 1. Good. Now, you have done some rearranging of the numbers. Now, look at the second rightmost bit. They do the sorting with respect to the second rightmost bit. Everything which is a 0 comes before everything which is a 1, and so on and on. So, how much time does this take? Bn once again, right, because for each bit you are spending time proportional to n. Partitioning will not be used, right. So, we will see how to do it. We will see, okay. So, it is not completely clear why Bn, but we will come to that argument also in a minute. So, first we need to understand what is sorting in a stable way. What does this mean? So, a stable sort is one in which if two numbers are the same, then after sorting, so if two keys are the same, equal keys, then after sorting their relative order remains unchanged, right. Suppose I have two numbers, so I have a collection of numbers, I have 1, 3, 11, 3, 5, right, these are my numbers, right. I have two 3s in there, equal keys. Now, if after sorting, of course after sorting this array would become 1, 3, 3, 5, 11, right, but the 2 3s that I have now, suppose with those 2 3s I had one was colored red and the other was colored blue, right, the first was colored red and the second was colored blue, then after sorting the red should appear before the blue, although they are still 3s, they should appear in the same relative order as was the case before we did the sorting, right. So that's called a stable sort, and we'll see why it is relevant here and why it is important here. Okay, so let's look at this now. Okay, so this is what we were sorting, and let's say we are sorting with respect to the rightmost bit. Yeah, so I have 4 keys with 0, right, they will all come before the 4 keys which are at a 1, which have the rightmost bit at a 1, but I would like that this appears before this. So the first number should better be 0 1 0, the next should be all the 3 zeros, the next should be 1 0 0, the next should be 1 1 0, which is the case here. I am not permitted to rearrange them. You know, if when I am saying I just sort with respect to the last bit, you could also create this array of post sorted in which this was the first number, but that would be wrong, that would not be a stable sorting. And similarly for the ones, the first should be a 1 0 1, the next should be 0 0 1, the next should be 1 1 1, and the next should be 0 1 1. This is crucial for the correctness of the sorting algorithm. If you don't do it this way, this will not give you a sorted sequence at the end. Okay, so everyone understands what stable sorting means. Okay, now let's understand the correctness of the algorithm. So we are now going to show that any 2 keys are in the correct relative order at the end. That means that if I take 2 keys, one is smaller than the other, yeah, okay, then in the end the key which is smaller appears before the key which is larger. Okay, it's a very simple proof. So suppose these are the 2 keys that were given to me. Let me look at the leftmost position at which they differ. Leftmost, right. So this, they don't differ at this place, they don't differ at this place either, but they differ at this place. Let me call this position K. Okay. Now when I am sorting these, when I am sorting this bunch of numbers, what's going to happen? I would have, when I sorted, so when I am sorting, remember I am sorting by considering first the rightmost, then the second rightmost, then the third rightmost, and so on. So when I considered, okay, let's understand this. So the claim is that at step K, the 2 keys are put in the correct relative order. So at the first step they are put in some, they are maybe rearranged, I don't care, right, they are put in some order. At the second step also they are put in some order, I don't know. But at the kth step, right, this key would be put before this key, because this is a 0 and this is a 1. Okay. So at the kth step the 2 keys are put in the correct relative order, but all's not done now. We want to argue that at successive, at the later steps, at the k plus 1th step and the k plus 2th step and so on, the relative order is not interchanged. यहाँ पे तो आपने इसको इस की के पहले डाल दिया array में अपने, but ऐसा नहीं होना चाहिए कि बाद में इस step के बाद में आप वापस गड़बड़ कर दें, पर ऐसा होगा क्या? Because of stability, so now when I am looking at the k plus 1th step, at the k plus 1th step these are the same, right, these are the same. So because it's a stable sort, this key which is appearing before this would continue to appear before this, yeah, and similarly at this next step and so on and on. So beyond the kth step the relative order would not change anymore. At the kth step you would get the right order between these 2 keys, the smaller key will appear before the larger key, and at subsequent steps this relative order would be preserved. The smaller key would continue to appear before the larger key. ये सबके समझ में आ रहा है? नहीं आ रहा है? So let's take an example. This is the two keys once again that I am considering. So initially they could be in some arbitrary order. I have in fact that the larger key is appearing before the smaller key. This is the array in which the numbers are, right? यहाँ पे और बहुत सारे numbers हैं इधर उधर. ये blue band signifies कि बहुत सारे और number हैं बीच में. ये बड़ा वाला number हमारा छोटा वाले number के पहले आ रहा है, right? This is location 0 of the array and so on and on. So we would like that the array keys be in increasing order, but right now the bigger number is appearing before the smaller number. When I am looking at the kth step, at this step when I am sorting with respect to this bit, the kth bit, I would have put 01011 before 01101 clearly, because at the kth position this is a 0 and this is a 1. Now when I am looking at the next more significant bit, yeah, I would continue this relative order, because the next more significant, at the next more significant bit they are the same. If they are the same, then stable sorting ensures that I have to maintain the relative order that was there till that point, in which this was appearing before this. So this will continue to appear before this in this step and in subsequent steps also. So because the sort is stable, the order of the two keys will not be changed when bits more than k are greater than, or bits at position larger than k are compared. Okay? You can also see now why I had to start from the right end. If I start from the left end, then this technique is not going to work. Okay? Take this as an exercise. Think of an example where if I were to start from the left end, this would not give me a sorted sequence at the end. Right? Now there is nothing sacrosanct about decimal binary numbers. I can also apply the same technique to decimal numbers. Right? So what do I do? First I sort with respect to the rightmost digit, yeah, which means that the ones would come before the twos, would come before the threes, and so on and on. Again the sorting is stable. Right? So after the first step, as you can see, the first number would be, so there is a 1 1, there are two twos here, and so on and on. So there is the unique one is 031. So 031 becomes the first number. Right? And then there are these two twos, 032 and 252, which should be the second number, 032, because it's stable. So 032 is the next, 252 is the third, and so on and on. So I sort with respect to this. Next I sort with respect to this. So there is a 1 here, 015, there is another one. So I'll first put this and then I'll put this. Yeah, and so on. And as you can see at the end I got a sorted sequence. Yeah. So now we need to figure out the time complexity. How much time are we taking? So how many passes, such passes are we making? We are making as many passes as the number of digits or the number of bits or whatever it is. Yeah. But we need to now see what we are going to do in one pass. How are we getting the ones before the twos, before the threes, and so on in a stable manner? How much time does that take? What kind of a scheme should we employ for that?
If we use this decimal representation
Yeah.
for the audio exchange that is sort,
Yeah.
and it will not work in the exchange that is sort will not work.
Exactly. So for exchange radix sort, we basically wanted to partition the array into two parts only, right? But here, because these are digits, not just 0, 1, it's not a two-way partition anymore, right?
So we cannot use exchange radix sort for directly
For decimal numbers, we'll have to represent it in a binary form to be able to do this.
It is like an insertion sort.
What is like an insertion?
This in place sorting. So stable sorting. So that you are, if you sort on the last one in a like insertion sort.
I don't quite follow what you're saying. We'll discuss this later, huh? Okay, so let's figure out what the time complexity is. For k equals 0 to b minus 1, we are sorting the array in a stable way, looking only at the kth bit. So suppose this could be performed in order n time, then the total time complexity would be order bn. Yeah, that's completely clear. Provided we can do this sorting in order n time. Which sorting are we talking about? We are looking at a particular digit. Yeah, one pass. We are looking at a particular digit or a bit, and we want to ensure that all the numbers, if I am looking at it decimal numbers, all the numbers are sorted based on that digit, right, the ones before the 2s before the 3s, and that the sorting is stable. Yeah. So we want to be able to do this in order n time, and the method of choice is what's called the bucket sort algorithm. Right? That brings us to the second sorting scheme that we talked about. Okay. So what is bucket sort? Lots of buckets. Okay. So we have n numbers. Each number is in a certain range. Let's say 1 through m. Right. So bucket sort is a stable sorting algorithm, and it will take time order n plus m. Right. You understand what we are talking of. So this is very useful when you have a large number of numbers with lots of duplicates perhaps, and the numbers are coming from a small range. Right. Then you don't need something like n log n time or some such thing. You can then do it in time order n plus the range of the numbers essentially. Okay, and let's see how this works. So suppose this is my collection of numbers 2, 1, 3, 1, 2. So m is 3, right, because you can see the numbers are in the range 1, 2, 3. So m is 3. There are 2 2s and 2 1s. So first what we are going to do is we are going to create m buckets, right, and you can understand what you will do in each bucket, right. Just take a number and throw it in the appropriate bucket. So we have these 3 buckets, one corresponding to each possible value in this range, and each element of the array is put in one of the m buckets. So these are my buckets. Take the first number, it goes into bucket 2, so I put it here. Sorry. Then I take the next number, it goes into bucket 1, so I put it here. The third number goes into bucket 3, I put it here. The fourth number goes into bucket 1, so I append it at the end of this list. End is important to maintain stability, right? And then I take this 2 and append it at the end, and now I'll just read the numbers. I'll take the numbers in the first bucket, basically append all of these lists. Yeah, so 1, 1, 2, 2, 3 and so on. So we'll put the elements from the buckets into an array and just read it off in this manner. So this gives us a stable sorting then. You understand why it's stable? Right, because if 2 keys are the same, then they would be in the same bucket, but we would also have put them in the right order. That's why we are appending. Right, if we were attaching at the front, then we would have to read it the other way around, which is the same as that. Okay, great. So with that, you should be able to argue that our straight radix sort takes order bn time now, right? We said for each pass we want to do it in order n time, and you can do it in order n time using such a scheme, using bucket sort. So you do that in order n time, and there are b passes and all, so it becomes order bn. Yes? You're going to get one question from this in the exam. Yeah? Okay, in place sorting. Yes? You want to know what the question is? Okay, so a sorting algorithm is said to be in place if it uses no auxiliary data structures. It could use a constant amount of additional space, however. And it updates the input sequence only by means of the operations replace element and swap. Basically it just, so you have a bunch of numbers, it replaces one of them by some other, or it just swaps 2 numbers. That's when we call the algorithm to be in place. So let's see which algorithms we have seen can be made to work in place. So bubble sort actually you've not seen, right? Or you know what bubble sort is? Huh? You don't know what bubble sort is? Okay, I'll not go into bubble sort then. Let's see. Okay, who can tell me heap sort? Is heap sort in place? So we can have one array and basically implement our heap in that array, and we are just changing the elements in that array. Merge sort, is merge sort in place? Why not? To merge two lists you need additional space, right? You cannot merge in the same list. So merge sort is not in place. Quick sort? Quick sort is in place because we partitioned in the same array and then we just did recursively left and right. Yeah? Okay. For merge sort, to do the merge, to merge two lists, you need additional space, because what were we doing in merge? We are taking the first element of the two lists, comparing them and putting it out into some other space. You can't just copy it back there, it would not work.
Is it just that if in an algorithm uses order one space, it is increased?
Yeah, order one space is okay, it's in place. Yeah, but not size, not space proportional to the number of elements. It should be independent of the number of elements. Okay, so you can look at the other algorithms and think of whether they are going to be in place or not. Radix sort, is the radix sort in place? But buckets, but the number of buckets is independent of the number of numbers. The nodes that we are creating, yes, that is additional space, right? So can you modify the scheme to make it in place?
So you keep counting every bucket, you just count the number of those elements that are in the array.
Yeah, you'll have to think about it. So think about this. Can you make it in place? Can you make radix sort in place? It's a good thing to think about. Okay, so let me get to the last topic that we are going to cover as far as sorting is concerned, and that is a lower bound for comparison based sorting, right? So what does comparison based sorting mean? It basically means that we are only looking at sorting algorithms in which all you are permitted to do is to compare two numbers, right? So suppose you have a bunch of elements, I am not even saying numbers now, and you want to sort those elements, right? I give you those elements. I have a comparison function which you have to use to do the sorting, right? So like your comparator, right? So you give me the two numbers, I'll tell you which of them is smaller than the other, because maybe these are not numbers but some objects, and I am the only one who knows how to compare these objects. Yeah. So that is a comparison operation. You give me these two numbers, I decide whether one is less than the other or not, whether the first is less than the second or the second is less than the first, and I give you the answer. Yeah. Now the question is, how many times will you have to ask me for a comparison? You understand? You wanted to sort these n numbers. How many times will you have to ask me? Maybe I charge you 1 rupee for every time you make you give me a certain comparison to do, right? The comparison is let's say an expensive operation. Every time you say compare these two numbers for me, I am going to charge you 1 rupee. So how much money are you going to spend? N log n. You have seen algorithms which would take no more than n log n time. What we are going to argue now is that there can be no algorithm which takes less than n log n time, n log n comparisons. No one can come up with an algorithm, right, so that algorithm will always take less than n log n, will take less than n log n comparisons for all inputs. For certain inputs it could take less than n log n comparisons, but for all inputs it would take less than n log n comparisons. That's not possible at all. Okay, so we are going to understand this in the following way. Let's look at a particular algorithm. Yeah. So you have a certain algorithm, and let's say your objects are sitting in some array, and your algorithm works on that array. So at the first step it's going to ask me to compare two elements of that array. Yeah, let's say those elements are at positions S1 and S2. Okay? So my very top node here is this node whether S1 is greater than S2 or not. Right? It's going to ask me this. And I am free to say whether one is less or whether one is more based on what my comparator function says. Right? So these are, so to say, the questions that the algorithm is asking me. First it asks whether it asks me to compare S1 and S2. If I said a yes, then it would have asked me for a comparison of S1 and S3. Let's say I have such a thing. If I had said no, maybe it asked me for a comparison of something else. This need not be S1, S3, it could be something else. Right? Depends upon what the algorithm is. But at each point it's coming back to me with certain comparisons, with certain numbers to compare. The first time it says something, then depending upon whether I say yes or no, the next step, the next comparison it asks me something else. Now depending upon whether I said yes or no, the next comparison it could ask me would be something else, and so on and on. So the execution of the algorithm is really a path down this tree. Yes? Right? Great. Now at some point the algorithm is going to stop, right? When it doesn't ask for any more comparisons, it says, well, I'm done, this is your sorted sequence, right? So which means that this path ends in this external node here, this leaf node here, which corresponds to a particular permutation of those numbers, right?
We are saying that every
This sequence of moves would have been made if, you know, if I had a certain ordering on the numbers for a certain permutation of the numbers. Okay, let's understand
There
this.
would be some finite criteria of the yes and no. I mean, when we go for a yes, then there would be some finite criteria, right? It is not necessary that if we say S1 is less than S2 and if it is a yes, then we are comparing S1 and S2. We can compare
We can compare anything, yeah.
anything. So
That depends on execution.
so that those numbers which we are comparing, that is randomized over the entire set. Any two numbers we pick up, randomized.
No. So there's nothing. So don't look at it that way, right? So we are saying your algorithm. You have a certain algorithm, right? Which has the numbers written in an array. Let's say 1 through n. At the very first step, it's going to come and make a certain comparison. Let's assume it's a deterministic algorithm. No randomization for now. Right? The same argument applies for randomization also, but for now let's assume it's deterministic. It will say, okay, compare, let's say first time it comes to me, it will say, look at the number in location 3, look at the number in 7 and tell me which is smaller. Whether 3 is less than the number in location 3 is less than the number in location 7, or whether the number in location 7 is less than the number location in number 3. Right? So I put a node here saying, let's say this array was S. So whether S3 is less than S7 is the first comparison it asks me for. If I had said a yes, I do not know. If I said a yes, it would go and ask me some other, to compare some other two numbers. It's your algorithm, I don't know what it's going to ask me. But whatever it's going to ask me, I'm going to put down here. Suppose it came and said S2 versus S5, whether S2 is less than S5. And if I had said a no, maybe it came back and asked me something else. It came and asked me S6 less than S13, maybe, right? It's your algorithm. Okay? So depending upon what option do I have an option of basically saying my yes and no. That's all I say. Yeah, I say a yes and then I say, you know, I can say a yes, a no, and so on and on, depending upon what I rate as the relative order of these elements in these array. Right? Think of these objects as some complicated objects. You don't know what their relative order is, so that's why you're asking me about them. right? And I have some way of figuring out what the relative order is. Maybe today I feel like that the relative order should be, based on GPA, that tomorrow I feel like relative order should be based on height or whatever it is, right? I can decide, right? And for that I would make a certain choices of yes and no, which would eventually end up in a leaf, in an external node of this, right? And so when you reach this, you say, well, I have sorted it, you stop, because this is all the comparisons you did. The question is, how many comparisons did you have to do? The number of comparisons is basically the length of the path that you took, the height of this tree. Yes? So how many comparisons would you have to do? How high does this tree have to be? Why n log n?
Because there are n factorial permutations of the array, so there has to be n factorial leaves.
Yes. So that's right. There have to be n factorial leaves in this tree. Now this is not a straightforward thing to understand. Right, देखिए, depending upon what these objects are, I should be able to get all kinds of permutations. Every permutation is a possible solution at the end. Every permutation of these n numbers. What is sorting? A sorting, you are given the elements like this, and eventually what do you generate? You generate a permutation of these elements? Yes or no? आप लास्ट में कहते हैं हाँ ये अरे मेरी सॉर्ट हो गई, ये मेरी सॉर्टेड अरे है. What is this? This is just a permutation of this set of elements. ये जो पहले यहाँ पर है वो कहीं और आ गया, ये जो है यहाँ आ गया, and so on and on. This is just a permutation of this. Now all possible permutations should be should exist as leaves. That depends upon what the relative order is, what I have picked as the relative order, right? So given a certain permutation, if that is what I picked as the relative order, then your algorithm should end up in that. If I took some other permutation and picked that as the relative order, then your algorithm should end up in that, and so on and on. So every leaf of this tree corresponds to a permutation. Yeah, and furthermore every permutation should be representable as a leaf. So which means that this tree has n factorial leaves. Yeah, it's not a complete binary tree, or it may be, it is, I don't care. I know it's a binary tree, right? It's a binary tree with n factorial leaves. So what is its height going to be? At least log of n factorial, right? So height therefore is at least log of n factorial, at least. ज़्यादा भी हो सकती है, कम से कम इतनी तो होगी ही होगी. Yeah.
So our order of the comparator, does it satisfy the symmetric or the transitive?
Yes, yes, it satisfies all of that. Even then, it can, I take a particular permutation of these elements and I say I am going to answer with respect to this permutation. All queries that are asked from me, I will answer with respect to this permutation that I have in my head.
So then, is it possible that suppose I have S1, there are three, suppose we take S1, S2 and S3.
Yeah.
And at some point in the tree we have some decision of related to S1, S2 and S2, S3.
Yeah.
And then other point in the tree,
Yeah.
other point in the tree there is a decision based on S1 and S3.
Yeah.
Now that cannot take both the paths, yes and no, because...
Yeah, I understand that, but that's not the point. The point, all we are trying to say here, is that
So it's not necessary that every node has
that I could have a certain permutation in my head. I could have a certain permutation in my head and I could use that to answer all your questions and it would be consistent. Yeah. So there have to be n factorial leaves, and if in a binary tree there are n factorial leaves, basically if there are some n leaves in a binary tree, then it has to have a height of at least log n. Right. So which means that the tree has to have a height of at least log of n factorial. So height of the tree is at least log of n factorial. This is roughly n log n, right, which means that there is a certain permutation. So what is the height? The height is the distance of the longest of the furthest leaf from the root. So if this is the furthest leaf from the root, then if this were the permutation, then your algorithm is going to take a time of at least n log n, or number of comparisons at least n log n it's going to take. Okay? So this is the argument. You can go over these slides once again and understand it more carefully. So this is the argument for why any comparison based sorting algorithm has to have at least n log n time. So recall, this is only, you are only permitted to compare two keys. Radix sort is not an example of a comparison based sorting algorithm, right? Because you are not comparing keys, you are going into the keys, looking at the bits or the digits, and so that's why radix sort doesn't have the complexity n log n. It could be less than n log n if b, the number of bits or digits, is less than log n. Yeah? So radix sort is the only such. All other algorithms have to have, because they are all comparison based sorting algorithms, they have to have a complexity of at least n log n, and there are many which achieve that bound. Yeah. So with that, I'm going to end today's class. So we looked at radix sort, we looked at bucket sort, we understood what stable sorting is, and finally we saw this lower bound on comparison based sorting.